Hello, my name is Rishi, and did you know that one of the biggest bottlenecks for deployment of new energy systems and nuclear energy in particular is not the technology itself, but the paperwork, the documentation, the safety, and the regulatory compliance associated with it? It takes a lot of time, a lot of manual effort, and a lot of money, which increase the costs of projects. And so, if you have to make these processes more efficient, we need new tools. Hello, my name is Rishi, and in this channel, I talk about my journey building Nova CDS. Using these videos, I share my progress, and hopefully you will learn about the licensing and new tools associated with nuclear power plants. Now, some of these things can be applied in other energy domains as well, but the focus is on nuclear because the regulatory side is very rigorous and the safety standards are very high. Today, I'm going to talk to you about Processforge. If you're new to the channel, please like and subscribe to it. Processforge is a project within Nova CDS, and the reason why we use Processforge is to enable simulations with modern codes and modern, let's say, tooling to ensure that the computation can be replicated. So Processforge is a very interesting project, and I've been working on it for more than a few months now. It's fully open source, so you can go to processforge.urjanova.com and you will see this website that you are seeing. Essentially, if you are really interested in what Processforge does and how it works, you can just read the white paper, as you can see here. And you can see it's a very short, let's say, a summary and an abstract. To cover some of the basics, what I'm going to talk to you about is how and why Processforge was created. Now, in the context of simulations, and simulations particularly in the context of nuclear engineering for fission, for fusion, and others, there is a lot of activity going on within the IAEA and in the broad open source community in general. One interesting project that is available, for example, is OpenMC. You might have heard of this project, which is essentially a Monte Carlo code, a community-developed Monte Carlo code for neutron and photon transport. Now, this gets into the details of nuclear engineering, but just to give you an idea, this kind of code generates data that you can then use to simulate processes and couple with other codes and so on. Now, at Urjanova, we are focused on the siting and the site aspect of nuclear power plants. And one of the things that you obviously have to consider when you are doing that is the associated, let's say, dosage requirements that the IAEA has, or the safety aspects of cooling and so on. So in that context, we use nuclear simulations quite extensively. And in that, OpenMC is a very, very important and a useful tool. It's a modern tool, so you can use all the modern systems like Docker and all kinds of things with OpenMC, which really is a breath of fresh air when you look at some of these codes, which are really very old. There is a large OpenMC community, and I can talk to you in great detail about the progress that has been done in OpenMC. Now, I also want to mention that OpenMC is not the only code that's out there. There are many, many others, and what we wanted to do was build some kind of an engine that allows simulations to be run in a deterministic fashion and also use the codes as necessary. So you will have, for example, a code called Festim that's available. There are other, let's say, coupled codes which include thermal hydraulics and so on. So the idea is that normally you do these simulations with coupling different codes, and this is a really manual and a time-consuming process, this exchange of data and so on. And so this is why Processforge was created. It introduces a very simple three-step workflow of, let's say, plan, init, and apply. So PF init, PF plan, and PF apply. So you take what is known as a flow sheet where you define all these parameters of the simulation, you initialize it, plan it, and apply it. In this way, you can then run OpenMC simulations from the console in a deterministic fashion. So in this video, I'm going to just introduce this workflow to you and show you some basic commands, and we'll get into details of how OpenMC simulations are run. Obviously, I would be very keen to hear from you about your experiences and feedback about this project, and grow it as you think it's most useful. So the reason for the creation of this project was a personal one. When I was introduced to OpenMC, it is not so easy to set up a working environment. You have to use, for example, Anaconda, the Conda developer environment, and other things. Recently, there have been Windows builds for OpenMC, but OpenMC has been traditionally a very specific way to run it. And so what I wanted was to not care about how the code is run. We set that up, and then all I'm interested in is the simulation, and most importantly, in the simulation output, which is the state point file that is generated by OpenMC. Now, of course, OpenMC is a tool, so you can wrap it around all kinds of processors, run it in the cloud, and so on. And so this was what I really wanted to do. But I took inspiration from a tool called Terraform, which is very popular in the cloud deployment side, and used those concepts here. So what we have is a flowsheet configuration, which is basically a YAML or a JSON file where you define your simulation parameters, including things like OpenMC parameters and so on. And you can keep that file under source control. And then you have this plan, apply, run, let's say, workflow that you can use to run the simulation and also manage the outputs. And in this, Processforge manages all of this. And as a side effect, you get some very interesting things like state management, like homotopy continuation, and also this notion of rolling back to a previous state of the simulation. So this state management of the simulation is very crucial, because when you have to run multiple runs of a simulation or multiple versions of a simulation, you can move it forward and backward. There are something called snapshots, which are stored in Processforge as well. Now, one of the other more interesting things about Processforge is that, as I said to you, OpenMC is just one of the codes that are available. There are many others. And we have this abstracted that out via what is known as a provider interface, where basically you can build an integration to a code of your choice and then implement it with Processforge. So you can see here, for example, we already have integrations with OpenMC and Festim, and then you can add others as well, couple them, and so on. So it gets really interesting. The other thing about this is since the state is managed with Processforge, the data can be, let's say, moved between one code to the other in a seamless way. Now, the reason why this is interesting is because you can use the same Processforge commands to manage data and get away from custom implementations of data management and so on. So there is a validation repository as well. And as I said to you, you can take a look at it on GitHub. So you can sort of take a look at the repository and so on. What I'm going to show you very quickly is how this plan, validate, plan, apply, run, and then maybe have a quick discussion on why this is interesting. So here you have Processforge has a concept of flow sheets. So here is a flow sheet. And here, for example, is a simple hydraulic chain that you are seeing. It's exactly what you would expect. It has some providers. In this case, we are going to use the Kunprop library, not the OpenMC library. You have materials, for example, water, steel, and toluene. So basically, you have these IDs. You can have material mixes, as you would expect with OpenMC type, let's say, code. You have streams and units. In this case, you have a pump, a pipe, a valve, a pipe that lets out of it, a strainer, and so you can lay out an entire plan to it. Obviously, this is all in JSON, but you can imagine a user interface around it as well. So this basic sort of a JSON file is a flow sheet. So you say to Processforge, initialize the flow sheet. You can validate the flow sheet. Basically, you have OpenMC, Festim, and other containers that are pre-built for you. So you can build your own Docker container with these libraries and Anaconda and all of that. And basically specify where to run it. Then you plan the sheet, which is the most interesting part about it, meaning you are sort of validating the configuration of the simulation. And because you're storing the state, you can check if it is different from one say state to the other. And then you press apply, which will then take that flow sheet and then run it in the cloud in the Docker container and all the other things that are interesting with it. So let's just take a look at a very simple simulation. So let me just switch to my other terminal and just continue there. So welcome back. Here is my terminal. I have downloaded the Processforge repository. I have sort of followed the instructions and installed the let's say the necessary libraries via UV. By the way, there is also a Python wrapper around it, so you can use it in your Python scripts. I'm going to use the CLI interface just to show you. Here, what you will see is essentially the hydraulic chain example, the flow sheet that I just showed you. It is extremely simple. You can have the units, the pipes, and so on. And now I'm going to initialize Processforge with it. So if I just say pf init, so by the way, Processforge has this shortcut of pf. So I say pf init flow sheets hydraulic chain.json. So just give it a minute. What it's doing is it's reading that simulation file, the flow sheet. You can see here while it's doing that, it has this mode of steady state. The final time is 20 seconds and the delta is 1 second. So all of the simulation parameters and let's say the components of the simulation are stored in the flow sheet. Here you see it created a config.json. It had the providers. This was a cool prop library that we're using, but if there was OpenMC or any other providers, it would have the containerized providers. And then it has a lop file that is also generated. Now let's try to do this pf init. And now we have pf plan, flow sheets, hydraulic chain.json. So if I do that, here you see it has read the flow sheet. It has sort of figured out what's in there. Here you have pumps and pipes and all the other, let's say, CAD aspects of it. You have feed streams and so on. And it has said there is no major problem in this flow sheet. It is structurally sound. It is doing, for example, this kind of state management internally as well. So here you see it is warning you that the product from pipe 4 is not consumed by anything. So that's okay. And then I just say pf apply flow sheets and hydraulic chain. So here, basically now what it is doing is that it has registered those units and it is now using coolprop to run the simulation. And here you can see that we can see the simulation has converged. Basically, the idea here is that because you're doing this over multiple runs, it will see if there is drift or not. And then it saves the outputs to a ZAR file, which is let's say an S3 compatible output format that you can then sort of use. Now, in the same way, this is just a simple, let's say, cool props and SciPy based simulation. You can create all kinds of steady state and dynamic simulations. I can talk to you about it in a different video, but I want to show you is what an OpenMC config file looks like. So if I go more flow sheets, eigenvalue, I think it's OpenMC, and it's eigen MSRE. So this is the molten salt reactor experiment, which is, let's say, familiar to some of you watching this. Essentially, it had, let's say, in this phase, there is the source is basically a simple source. Here you have, for example, the provider type, and the URL is localhost 9001. So there is a specification for a Docker container that you can build OpenMC and pass these variables into. So you can take a look at the repository. Here you have the materials defined as graphite, iron ore. This is directly from the molten salt reactor experiment. If you're familiar with that, this should look familiar. Just a JSON dictionary of the parameters. Then you have the steam. And the most interesting thing is this units component, which is the OpenMC solver. This is via the provider interface, which gives you essentially the simulation parameters like batches, point source. In this case, it's a sphere point source for the source. And then you have the definition of the tallies. And the simulation mode is steady. So what I'm trying to say to you is that we have containerized and wrapped the OpenMC runtime and the library in a Docker container. We have extracted the settings and the definition of the simulation in a JSON like this, and we are using Processforge to orchestrate this simulation. And all you then have to do is to change parameters in this file, and all the backend will be taken care of, and the state management and so on will be taken care of. And this is an OpenMC configuration. The next time I'll show you the Feston configuration as well. You can imagine putting something like this in a CI/CD pipeline, or sharing, let's say, simulation files as JSON, and the execution and the orchestration is managed by a tool like Processforge. In the context of Nova CBS and Origin Nova, when we have to calculate, for example, the dosage that is perhaps exposed in a site, or calculate, for example, the thermal hydraulics of certain components when it comes to regulatory submissions, we use tools like Processforge because we are more interested in the configuration and the outputs and making sure that the output is correct and correctly configured, rather than have to deal with OpenMC settings, let's say the containerization and so on. And so with this way, by putting these JSON files on GitHub, we can very easily manage our OpenMC simulations just like you would manage infrastructure by Terraform. So I hope this was useful. Please feel free to comment and tell me what you thought, how this can be improved. If you have let's say, some kind of a flow sheet like example that you want me to try, I would be very happy to try it and share with you some of the results and the details. If you go to processforge.orginova.com or go to the GitHub, I would be very happy to just engage with you and the broader community of how this can be built out. With this, we conclude this week's video. Thank you so much. I'll talk to you in the next one. Bye.